So the idea is, spectrum splitting, as we will talk about today, is an approach to increase the efficiency of solar cells. And of course, let's first lay the groundwork for why this is important. The proliferation of photovoltaics really depends upon the adoption, right? And the adoption, of course, depends upon the cost. So the fact that someone chooses a solar panel is almost entirely is driven by cost. You could probably ask your family and other folks you know. So if you look at the breakdown of costs in a very rough fashion, and many of you have looked at these as part of your projects in more detail, what you see is something is interesting is that the module itself costs a little more than 50%. These numbers are a few years old, so they're probably a little bit lower now. But something like roughly a little more than 50% of the overall cost is the module itself, which includes, of course, includes all the parts and all the solar panels and so on and so forth. But there's a big part of the cost, which is what's referred to as BOS, balance of systems / installation. This is everything else, which is not the actual module itself or the power electronics, which you can see is a small segment as well. These things include things like transportation, regulatory costs, so for instance, if someone has to install this on the roof of a house, one has to get permits from the local government, whether it's a city or county. Then you have to pay the roofer to go up there, get it all prepared, install it. You need electricians and so on and so forth. All these costs add up essentially to a little bit less than 50%. So an important question can be asked, is there something we can do that will make a big difference to the balance of systems installation costs? Because a lot of what we have talked about, for instance, in thin film solar and so on, has to do with reducing the cost of modules themselves, but we didn't really talk about the other side. So, a big conclusion is that the module efficiency makes probably the biggest impact. And how important is this? This has been studied many years ago now, almost 10 years ago, by Ken Zwiebel at George Washington University, where the analysis was done on cost of power at the DC power, which is shown on the left-hand side here. Is dollars per watt DC, varying from 0 to about $4 per watt. And here, the horizontal axis here is efficiency. So clearly, as expected, as efficiency of the panel increases, the cost per watt decreases. Now, the rate of decrease is different for different situations, which is what's color-coded in these legends. So you can see the residential is the highest cost. Then there's the commercial tilted, commercial flat, and the lowest is actually the lowest is non-tracking ground installation. But you can see the progression here where you have a two-axis high concentration system and so on and so forth. Now, in all cases, the efficiency is very important. Now, he made a very interesting statement at the bottom here, which is important for us to kind of sink in, is that if you think about a low efficiency module, a 5% module, even if you gave it away for free, it would, or if it costs nothing, so it would still need to have a system price that the cost of power of $3.50 per watt for residential rooftops as a 15% module costing about $1.5 per watt. Now, what does that mean? That means that if you are a module manufacturer, you can charge, if you have a 15% efficient module, you can charge $1.50 per watt for that module. However, and that would be equivalent to giving away for free a 5% efficient module. So the efficiency itself can make a pretty big impact on the economics, clearly. Of course, the efficiency is also important because in order to, let's say, meet the power requirements of a home, if you have a more efficient module, you need fewer of them, right? So which means that your installation is cheaper, your transportation costs are cheaper, and so on. And you need to, only modify a smaller portion of the roof and things like that. So it makes a big difference. You can also look at this in a slightly different fashion by plotting the module cost. So in this case now it's dollars per meter squared because the module cost goes by area as a function of the levelized cost of electricity. In other words, what is the expected cost of electricity output from this from an installation. Now, this is a little bit different than dollars per watt because here you're talking about energy output, which is kilowatt hours, which is power times time, right? So it's averaged over some utilization time, a year typically, or several years. The lifetime, typically it's the lifetime of the panel, which can be 30 to 50 years. So here you see various plots, and as the efficiency of the module increases, this plots become more vertical, which is great because that is saying that you can the module cost has lower effect on the levelized cost of electricity, which is what you want, both as a consumer and also as someone who might be selling the modules, because it just means that if you have a more efficient module, you can sell it for a higher profit margin, for instance. And as a consumer, this is good because you only need to purchase fewer modules to get the same amount of power. So from the Department of Energy standpoint, this actually has changed, but this was the planning target, about 6 cents per kilowatt hour. By the way, if you open up your Rocky Mountain Power electricity bill, you will see a number which is lower than this, but that's the number that people are trying to meet. Of course, from coal, it's quite a bit lower, but it depends on the jurisdiction, and also, as we talked about in the very beginning of the class, depends also on the time of the day in certain markets. So like in Germany, the power actually fluctuates based on the time of the day and the day of the year and so on. Now, then let's think about what limits the efficiency of a solar cell. And you saw this in a little bit in the lecture from Rujan. A single band gap, which is what most solar panels are made out of, does not match the solar spectrum. So this plot is the solar spectrum. The horizontal axis is wavelength. The vertical axis is the relative spectral output. So you can see that the light from the sun is extremely broad. As we've seen before, it's a black body. It's in a huge range of wavelengths, everything from UV down here to the infrared and even beyond, right, into the mid-infrared and so on, which is where you get the heat. Now, the problem with this is that if you use a single bandgap solar cell to absorb these photons, they're not very efficient. And let's try to understand why from a fundamental perspective. Now, where does this energy go? Now, let's imagine a solar cell, which is essentially a semiconductor material with 2 bands, as shown here. So let's just zoom in here for the sake of discussion. Of course, this is a very simplified picture. We have the valence band, which is filled with electrons, shown by these solid circles. And then we have the conduction band up here, which is filled with what we call holes, which are essentially vacancies of electrons, or in other words, those are energy levels that the electrons can occupy. They're waiting for an electron to occupy. Now, when an incident photon comes in with some energy h nu, now keep in mind that we also have something called the band gap, which is this for the semiconductor, Eg, which separates the valence band and the conduction band. Now, when the incident photon comes in with an energy h nu, there are many things that can happen. So let's look at the possibilities. First, let's imagine the condition where the h nu is exactly equal to the band gap. This is the ideal situation. The photon has just enough energy to kick an electron from the valence band into the conduction band, So the photon essentially disappears, it annihilates, and its energy gets transferred to the electron, which now gets increased in energy into the conduction band. Increase in is now is potential energy. Just keep that in mind. And that's great. Now you have an electron here, which can move around in the conduction band. And this can go to terminals to charge a battery or charge a car or whatever, right? Or use it to run a motor or run create light or whatever. Of course, holes also go to the other terminal. Right, so this creates a current. This is a current. And because of the voltage difference between the electrons and holes, you have a potential difference. Current times voltage gives you the power. So we know this. Now there are other things that can happen when the energy of the photon, for instance, is less than the band gap. If the energy of the photon is less than the band gap, nothing happens. It doesn't have enough energy to kick the electron into the conduction band, so it just passes straight through. This is what we refer to as non-absorption loss, so the material is simply transparent. A good example is glass is transparent to visible light, right? Glass, the band gap of silicon dioxide, which is a primary component of glass, is much larger than that of visible light. So visible photons simply pass through, nothing happens to it. So the glass does not create current from visible light. You have the opposite situation where the energy of the photon is much larger than that of the band gap. Then, of course, the photon has enough energy to kick the electron in from the valence band to the conduction band, but it has a lot more energy. What that means is that you can have many situations that can happen. But one of the extreme situations that happen is that an electron from deep inside the valence band, which means it has lower potential energy, can be kicked way up into the conduction band with much higher energy. But now what happens is that the quantum mechanics dictates something called rapid thermalization, and we won't go into why that is the case, but essentially you end up losing this energy very, very, very quickly, so as the electron relaxes down to the edge of this band, and the hole relaxes down to the edge of this band, and this is lost as heat into the crystal structure and simply heats up the solar cell. And it's actually very bad for many solar cells because the efficiency typically drops with increase in temperature. So that's something called thermalization loss, as we're shown here. And then there's, and once it relaxes, of course, then it can go to the terminals and drive current, right? And then produce power. I times V gives you power. So that's the same as this situation B here that we talked about. Now, there's one more thing that can happen is, let's assume in this case and in this case, instead of going to the terminals and producing current, you can also have something called radiative recombination, where the electron simply combines with the hole, as shown by this arrow, and simply annihilates. This electron hole pairs disappear. The electron goes back into the the electron disappears from the conduction band and simply goes back to the valence band. And in return, the energy is simply emitted as light, which is this H nu photon, and which is the example of fluorescence, phosphorescence, and things like that. So a good solar cell, as you probably saw in the lectures from James, is also a good LED. So this is a very interesting thing to keep in mind. A high efficiency solar cell like gallium arsenide is also a high efficiency LED. Now, there are lots of caveats in what I just said, but in the interest of time, we don't have time for it. But if you have questions, we can talk about it later. Now, you can also think about an allocation of where all the different loss mechanisms are. And there's a very important paper written by Atwater and Pullman back in 2012, which looks at the thermodynamic limits of a single junction solar cell. And it's a very useful paper for anyone who wants to delve deeper into it. So we can start at the bottom here. So the efficiency is here, and they're divided into different chunks as shown here in different colors. So first, you have a conventional single junction solar cell. This is the thermodynamic limit of efficiency that you can get, which is slightly about 30%. Now, all the other loss mechanisms are in blue with different colors shown. The entropy losses are in dark blue, and the energy losses are in light blue. So you can see that there's entropy loss due to incomplete light trapping and reduced quantum efficiency, entropy loss due to lack of angle restriction, which, by the way, has to do with the fact that a LED, as it emits light, the light is trapped, the emission angle is restricted to the escape cone, as we know. Whereas in the case of a solar cell, in theory, you can collect light from all the angles. There is no such restriction because you're going from a low index material, which is air, into a high index material, which is the solar cell itself. Then you also have entropy due to something called non-reciprocity, which we won't really talk about. It is related to thermodynamics, and then there's something related to loss and absorption or emission, which is something we just mentioned, where the photons don't have enough energy to get absorbed; they just pass straight through. And then there's an emission loss, which is the radiative recombination that we talked about in the last slide. Finally, there is an energy loss due to thermalization and lack of absorption, which is, of course, the biggest chunk of this. So you can see the biggest loss mechanism is this part. And that's the loss mechanism that we want to address with spectrum splitting. Because it's such a big part, we expect to make a big impact by addressing this. So that's what I want to talk about in today's lecture. Again, the loss mechanism, just to remind ourselves, is the fact that if the photon does not have enough energy, it will not be absorbed. This is the lack of absorption. And if the photon has too much energy, then you will lose that excess energy as heat because of this process called thermalization that we also talked about just now. So these are two phenomena that cannot be avoided without doing something special to the light that comes into the solar cell. So this has been known for a long time, and one of the conventional approaches to overcome this limit is something called the multi-junction solar cell, which you also have heard of before. But the idea would be to, instead of having a single junction to absorb the light, you have many junctions here. So in this example, we have a top cell, which has a high band gap, 1.86 eV, so it absorbs the high energy photons shown by this blue part of the spectrum. Then there's a middle band gap, a 1.4 eV, that absorbs this green part of the spectrum. Okay, that's the middle part of the light, slightly lower energy photons. And then there's a bottom cell, which is the third part of the sandwich, which has lowest energy, and that absorbs this pink part of the photons, which is the lowest energy photons. So you can see what happens is that for the top cell, because the band gap is so high, these green and so let me just draw it. So if I were to draw this, the blue photons will get absorbed in this layer, and the green photons will pass through this layer because the band gap is higher than the energy of the green photon. And the red photons will pass through both the top layers because the band gaps of both of them are lower, are higher than the energy of the photons, and get absorbed to the bottom. So by separating out essentially the colors of light in as shown here, you can actually extract more of the photons into electricity. So this is, of course, very nice because now you can get very, very high efficiencies. In fact, the world record of something like 42, 43% is actually obtained with such a solar cell. Now, oops. Why is this? Sorry, my program is, sorry about that, it's crashed. So this is where, let me just restart it. Okay, this is, okay, let's find it again. Those multi-junction cells are very important because they are used where efficiency is the most critical thing. And for example, in space. So the Mars rover, for instance, would use solar panels, which are like that, because in that case, of course, the weight of the solar cell is very important, and because of the launch costs, and you don't have a lot of room on the Mars rover to incorporate it. So, okay, so I'm waiting for it to reload. It's a little slow. Okay, it's opening up. Okay, good. Okay. But there are many problems with this approach. So let me point out why, what the problems are, why this is very expensive. First of all, if you think about these sandwiches shown here, so you can think about this as these sandwiches. You have different materials. So for instance, you have something called indium gallium phosphide, and you have something called indium gallium arsenide, and then you have something called germanium. These different crystals have different crystalline geometries, and at the boundary here, they need to match up very well. If they don't, then you end up with causing defects. So for instance, if this top, let's say, is indium gallium arsenide, I'm just saying as an example, and then the bottom, let's say, is germanium, you can see because the lattice structure of germanium is slightly larger than that of indium gallium arsenide, you end up with this kind of a defect as shown here. You can see that, right? And the problem with this defect is that when the electrons that are generated, when this atom, for instance, absorbs a photon and an electron is generated, the electrons can very easily go to these defects and get trapped, and they do not contribute to current. And that's a big problem. This is a big loss mechanism in these kinds of devices. So that means you have to be very careful how you make these materials, and typically they have to be grown one molecule at a time in extremely controlled conditions. So it's very slow, very, very expensive. The second problem is current matching. So if you think about how these three cells are attached, they are connected in series. So you have three cells essentially sitting on top of each other, as I showed before, and this cell is producing current, and this cell is producing current, and this cell is producing current, and they're all connected in series. So think about this essentially as a diode, which is connected in series with each other. So there are three diodes which are essentially connected in series with each other, photodiodes. This is exactly what the solar cells can be modeled in circuit theory. And then you have resistances associated with each as well. Now, the problem with this is that because they're connected in a series, the current is fixed. In other words, each solar cell has to produce the same just because they're connected in series, and the voltages add up, as we know from undergraduate circuits. And this is problematic because each solar cell might not, in its optimum condition, might not be producing the same current. For example, if you look at the solar spectrum, there's quite a lot of photons in the visible part of the spectrum, so one would expect the top cell to be producing the most current. However, it has fewer photons than the red part of the spectrum, so this produces the most current. Now, however, because the top part of the cell is only producing this much current, as shown here, the bottom part of the cell is prevented from producing the excess current, as shown here. So this excess current is actually lost because you don't have an optimum working condition for the bottommost cell. And this is the problem. This is obviously an unavoidable loss unless you put these in parallel, which of course in this kind of a configuration where you have a sandwich cannot be done easily, let's say. So all of this makes it a little more expensive. So then I want to spend a few minutes or maybe a minute or so and ask you, how would you solve this problem? And feel free to talk loudly if you want, or think among ourselves. It seems like we're a fairly small group, but I'm going to ask you to volunteer some solutions. Let's. So again, the problem is that the solar cell does not match a single band gap, and even if you used multiple band gap materials, the solar cell still doesn't completely match it because of these problems that I mentioned. So I want you all to think about, how would you solve this problem before I go into some ideas that we have been working on to solve this. Okay, anyone want to volunteer some ideas? You can all hear me, right? Hello, can everyone hear me? At least say that. Yes, okay.
A prismatic material on the top to separate the wavelengths, and then put the different bandgap materials side by side.
Yes, that's a good idea. That's would be an option. Do you recognize any problems with this idea? What you just said, was it Cedric?
Yeah, you're probably gonna have some losses in the material that splits the wavelength.
Yes, because it's not a perfect splitter, and it'll probably reflect some light. That's correct. One advantage of what you said is that the cells can be connected in parallel, so you don't have the current limiting issue that I mentioned before. Are there any other ideas, any other approaches that one can think of? Sorry, my thing is very unstable today. Anyone else want to chime in? Okay, it's fine. I think there are lots of options that people are working on. I'll talk particularly about one solution, which is very similar to what Cedric mentioned. And the main reason I'm going to talk about this is because this was a solution that is pursued by my lab. But treat this as an example. I'm not saying this is the only or the best solution. So the idea is very similar to what Cedric said. Basically, we have a device that we call a polychromat, which is kind of like a prismatic device, as you mentioned, which essentially separates the colors of light. So in this schematic where we're showing, we have two different colors. We have a red and blue. So red part of the spectrum goes to the left-hand side. The blue part of the spectrum goes to the right-hand side. And you can also see it does one more thing. It also does concentration of light. So you can see that this polychromat has a large input area, kind of like our CPC, and the solar cells are somewhat small. So it is doing both spectrum splitting and concentration at the same time. And clearly, of course, you also need to track the sun because of the fact that you are doing concentration, right? So for instance, if the sun, in this example, even though I drew these arrows in a curved fashion, this is assuming normal incidence light. Now, if I come in at an angle, of course, these spots will move, so I need to essentially track the sun. Now, these are designed in the form of micro optics. So this is an example of a design where we designed these multi-level structures which look like these buildings or Manhattan-like geometries as shown here, but they're relatively small, few microns, only a couple of microns thick, a few microns wide. And what it does is shown on this plot here, but you can see that the short wavelength light is primarily concentrated over here, and the long wavelength light is primarily concentrated on the right-hand side. So this is position on the horizontal axis and wavelength in the vertical axis. And you can, of course, also simulate the efficiency that can be achieved at the optical efficiency, which is, again, something Cedric mentioned, that you have some losses associated with doing this procedure. So you can also calculate the efficiency. So how efficiently can you actually separate the colors? So this is showing, what is the efficiency as a function of wavelength of the light that goes to the left-hand side or the light that goes to the right-hand side. And you can clearly see there's a peak by the left-hand side for the short photons, small short wavelength photons, and there's a peak on the right for the long wavelength photons. In this example, the average efficiency is something like 74%. Now, we actually fabricated these devices. This is examples of fabricated devices, which are quite interesting and pretty. So you can see the bright field image, dark field image, and they look like piano keys, but they are essentially these little bits of polymer, and they're very, very, very thin. So this is only about 10 microns, and again, just a couple of microns thick. And these are made by a manufacturing technique called grayscale lithography, where we essentially take a focused laser beam on top and illuminate a material called photoresist, which is photosensitive. In other words, it's sensitive to this wavelength, UV wavelength. And by controlling the amount of energy you put into the photoresist, you can develop a way different thicknesses of the photoresist, as shown here. So which creates these distinctive height levels with varying exposure times. And by doing a very controlled experiment, you can essentially create structures as shown here. You can also imagine doing this at high volume manufacturing. And interestingly, these approaches are actually used to make so first, let me explain this method of manufacturing. So you first create a master pattern, which is typically on a drum. In this example, I think it will be on this drum here. So its pattern is here. And the this spool, which is in a film form, goes straight down, is heated up. Oh, actually, sorry, this is the embossing drum, my mistake. So you can see the pattern is shown here with little black regions. And that pattern is embedded onto this film after it's heated up, and it passes through this drum, and then it's laminated onto a substrate. By the way, if you ever look at a $100 note, you will see a really thin strip of essentially a holographic feature. If you look at the $100 note, this is made in exactly this fashion by a company called Crane Currency out of in Massachusetts, actually. So in any case, yeah, so these techniques are actually used to make very large volumes. So in order to prove that these things work, we have to build, we can of course do this in sunlight, we can take it outside, but the sun is not a very reliable source because you have cloudy days and it cannot be controlled very well. So we have to build an artificial sun, which we call a solar simulator. And in my lab, we built something which looks like this, which is I would say a poor person's solar simulator. We simply have a white light lamp, which is shown here, a fairly powerful lamp, and then we have some simple optics to let the beam from the lamp essentially expand over a very long distance. So this is kind of simulating that the sun is really far away. Using a few mirrors, we let it bounce around over something like 3 to 4 meters. And then we place the polychromat over here, and then we have some solar cells over there, which you can see pictures of. So there's an example of what the device looks like. It's fabricated on a piece of glass. And here is the image, which is formed after the light propagates for some distance, which you saw in the illustration before. So in this example, we separated out the visible band and the infrared band. So the visible band looks white because all the wavelengths are there to a human being, and the infrared band looks dark because the light's essentially invisible. You can't see it. And there are several periods of this, so we repeat them 3 times in this example. We can actually characterize this quantitatively by putting a spectrometer in the image plane and essentially scanning it, and then we can generate images like this. So the left-hand side image is something you saw before. Again, just remind ourselves what's happening is that you can see, oops, let me pick a different color. You can see all the short wavelength photons are going here, and this is position on the horizontal axis, and the long wavelength photons are going here. So you're separating out the colors, and indeed that's what you see in the actual experiments as well. So that's pretty good. And you can actually measure the efficiency, and they're pretty close. In this example, we simulated something like 74%. We measure about 70%. Now, of course, at the end of the day, we want to put in the solar cells and measure the electricity output from the cells themselves. So in order to do that, of course, we have to pick the cells. So we pick the cells based on, first of all, we design the optic based on the cells we pick. So we first pick the cells and then design the optic in order to split the spectrum based on the band gaps. So the cells are split, the spectrum is split based on something called the external quantum efficiency curve, which we talked about before, which shows how efficiently is a photon of a certain wavelength absorbed. So in the case of gallium indium phosphide, which is the blue curve here, photons are absorbed up to about something like 675 nanometers or something like that. Beyond that, nothing is absorbed because the band gap of gallium indium phosphide, which is this material, is very high. So only high energy photons can be absorbed, as I mentioned before. But on the other hand, gallium arsenide, everything can be absorbed up to about 900 nanometers, which is where its band gap is. So that's where we used to split the light. We split the light around there, which is roughly the visible part of the spectrum. So this is roughly visible, and this is what's referred to as near infrared or NIR. You can measure first we measure the current voltage measurements. And of course, the current is negative, as you recall from circuits. If a solar cell is a photodiode, which is reverse biased. So when the current flow, when light hits it, you generate electron hole pairs, which can then flow in the opposite direction of the applied voltage. So that's why this current becomes negative, right? And then you have the voltage, and then you get a curve which looks like this. Is the actual measurements, and you can do this at gallium indium. This for the two different materials, and you see that the gallium arsenide produces more current because you can see it can absorb more of the light, right? It has a larger absorption, as shown here. Also, it has a higher, actually has a lower open circuit voltage, which is a little harder to see. But if you look here, the open circuit voltage, which is the voltage when the current goes to 0, is close to 1, whereas here it's close to 0.85. So you can see the gallium indium phosphide has a higher open circuit voltage than gallium arsenide, as expected, because this has a higher band gap, right? As I just mentioned. This is a slightly different polychromat that we use for this. So again, this is a spatial spectral image, as you saw before, and the efficiency. So this is pretty high efficiency, but this is the important result. So here you see what happens with and without the polychromat. So without the polychromat is the reference, and with the polychromat, in this case, the simulation, you increase the current quite dramatically, actually, something like 50% increase in the case of gallium indium phosphide, smaller increase in the case of gallium arsenide. You actually, interestingly, also increase the open circuit voltage slightly. This has to do with the fact that you're concentrating the light. Of course, what's more interesting is the power, which is essentially you take this data, this is current, and this is voltage, and power is simply current times voltage, and then you plot this power versus voltage, and you get a curve which looks like this. And in this case, we take the absolute value because we're looking at the power as a positive, which is work done by the system. If it's negative, it's work done by the system, but for the sake of plotting, we're simply plotting the positive values. Again, you see the reference and the plot with the polychromat, you could see a pretty dramatic increase here. In both cases. If you average both of them, we see a predicted increase of something like 28%, which is pretty significant for most situations. And these are actual experiments where the devices were made. Again, these are the pictures that you have seen before, so I'll skip that. And these are measured efficiencies. But this is what's interesting. So again, here you see the polychromat, and here you see the solar cells. These solar cells were made at the National Renewable Energy Labs out in Golden, Colorado. And you can see the gallium indium phosphide and the gallium arsenide. These are fairly expensive materials, so they're very small cells, as you can see there. And we measure each one separately. And we do indeed see an improvement in excuse me, performance. So here you see an increase in the current, as expected, slight increase in the open circuit voltage, again increase in the current in the other cell, also a slight increase in the voltage, and more importantly, you see an increase in the power as expected, and we measured something like a 16% increase in the total power output, which is again quite nice, but not as good as the predicted theoretical limit, which has to do with experimental errors, obviously. And I won't talk much about the discrepancies here because it's necessarily related to the class. But then the question is, how much more can we do? Okay, what sort of efficiency is actually possible? Now, it turns out this is an old idea. This was actually studied by there's a very important paper by Henry out of Bell Labs. I think this was in the early 1980s, where he calculated essentially what is the possible efficiency of a solar cell by either doing spectrum splitting or using multiple band gaps. From his model, he was agnostic to the mechanism, but the idea was if you were able to essentially separate the solar spectrum into little chunks, what is the best you can get in terms of efficiency? It turns out it is quite high. So this is the plot, and the plot simply shows the energy of the photon from the sun as a function of the the horizontal axis is the energy of the photon from the sun, and the vertical axis is the density, or how many photons are there coming from the solar spectrum, as a function of per unit area, per unit time for that particular energy, accumulated up to that energy. So that's why it goes down like that. In any case, it's summarized in this table in the inset, which says he used a concentration of 1,000 suns for simulation, and shows that the one band gap limit is about 37%, slightly larger than what we talked about before. But interestingly, by increasing the number of bands that we use to absorb the light, you can drastically increase efficiency, even up to something like 70% or so, which, by the way, would be quite dramatic if you're, because remember, today our solar modules are something like 20%. If we can increase that to even 30 or 40%, would be a dramatic change in the way solar panels are used. So we actually did this analysis with the polychromat in this example with 4 spectral bands. Of course, the more the number of spectral bands, it becomes harder and harder to do this very efficiently. So we did this example of 4, again, only in simulation, and showed that we can actually potentially fabricate and do this. Now, of course, optic is only one part of the problem. We also need the different bandgap materials, which turned out to be a much harder problem. So that's kind of the challenge associated with this approach. But hopefully, I've given you an idea of ways that you could think about increasing the efficiency and essentially going beyond single junction efficiencies. So that concludes the first part of this lecture, and I will stop here and give you a minute or so to see if there are any questions before we jump into the next lecture while this is loading. Also, don't forget that we have the final assignment is due on the last day of class, which is the week after next, which is a week after Thanksgiving. Now I'll talk briefly about the schedule. So in the second half of this class, I want to talk about something more practical, which has to do with how do you measure the different characteristics of photovoltaics. It's not necessarily directly related to optics itself, but there are some very interesting considerations from optics that you should be aware of as part of this class. So hopefully, once it loads, yes, my app here is really slow today for some reason. Okay, hopefully that's fine. Okay, so the first we need to understand what are we trying to measure in the case of photovoltaics. We'll focus on photovoltaics for the purpose of this discussion. First, of course, as I said just now, we typically measure current versus voltage, and this is what the plot looks like, right? Yeah, the current is negative because of the reverse biased nature of this of the solar cell, and the voltage goes to the right. And then there's these things that we talked about, which is the open circuit voltage, right? The open circuit voltage. And then there's a short circuit current. So this SC refers to short circuit, right? And this OC refers to open circuit. So this is the voltage value here when the current is 0. So that's the open circuit. This is the short circuit current, is the current when the voltage value is 0 because it's short circuit, right? The current voltage is the same on both sides of the terminal. And in between, and either of these situations are bad, you don't want to operate on those situations because here there's no current, so power is 0. Here there's no voltage, so the power is 0. So you want to be in between, and the optimal working point in this example is somewhere here, which is where you get the maximum power. And the fill factor, of course, which you've seen before, is how square is this curve, because a square curve gives the most efficiency because it's the voltage times current. So the more square the curve is, the better the solar cell itself is. It's a simple way to think about this. Now, efficiency is defined as the maximum output power divided by the input power, which we've talked about quite a bit in the context of the CPCs. And the fill factor is simply the maximum output power divided by the square, the area of the square, VOC by SC. This is simply the power curve. So we've seen this power curve shown by this curve has a peak value, which is the optimum operating condition. Now, of course, the spectrum is very important when we measure this for, because now this is a commercial product, when people need to provide standard measurements. So these standard measurements are based on some standard spectra. Again, we talked about this before. In the case of terrestrial applications, there's a specific intensity, approximately 1,000 watts per meter square, and there's a specific spectrum, which is defined by a standards community, also measured at 25 degrees Celsius. And there are different situations. So if you have a concentrator, then of course the intensity is higher than if you have space, and so on and so forth. So the area definition is actually quite important for efficiency measurements, because company A might say they have an efficiency of 25%. Company B might say they have an efficiency of 21%. But if they're measuring it two different ways, then this cannot be compared. So we need to have a way to compare them. In the case of non-concentrated cells, typically the entire area of the cell is used, including the area covered by grids and contacts, because those are considered area of the cell. For concentrator cells, it's a bit more complicated, but typically the area illuminated by the aperture is used. Of course, in this case, spectrum is also quite important. We'll come to that shortly. Many places do certification of efficiencies. There are a few labs in the US. National Renewable Energy Labs is one of them, based in Colorado. There's one in Germany, there's one in Japan, and there's a few other places, I think one in China and so on. which actually performs these measurements with very calibrated sources. The calibration is typically done with the reference cell whose short circuit current has been very, very carefully measured against a known spectrum. Of course, the air mass is important. We talked about the importance of how power changes as the sun moves across the sky. AM 1.5, which is halfway in between the noon at equator, which is the zenith versus the horizon. So this AM 1.5 is used as a standard. The importance of spectrum cannot be overemphasized because this is something it's a little bit not well understood. But it's important to consider spectrum when talking about efficiency, because we know that the current density, short circuit current density, is actually dependent upon spectrum, how many photons are actually coming in and what is the energy of each of those photons. So this is a fairly complex measurement, but just to give you a simplified version of how this can be done is we can measure the, excuse me, first we can measure the short circuit current density of the test cell under some source spectrum, okay, some spectrum. We can also measure, it's like the sun, for instance. We can also measure the reference cell under a reference spectrum where you know the spectrum very well, okay? And then we also have a calibrated cell, which is a reference cell, under the source spectrum. So this is, this is the reference cell. The top is the reference cell under the reference spectrum, bottom the reference cell under the source spectrum. So you can buy this reference cell, for instance, calibrated by some lab, and they will give you these values, and you can also measure this under your own source, and then you scale the measured short circuit current density by this ratio. Of course, this magnification M is simply the difference in the spectrum, the spectral mismatch. Sorry, it's the spectral mismatch factor, which is simply measuring the difference between the source spectrum and the response of the cell to the source spectrum, and the response of the reference cell to the reference spectrum and the source spectrum as well. So simply a mismatch factor between the spectra. I just want you to be aware that these differences exist, and something you should be aware of if you ever work in this field. There are other things to keep in mind, things like current voltage artifacts. In the case of solar cells, there's something called hysteresis, where you apply the voltage, you measure the current, you apply the voltage, measure the current, you're changing the voltage, you're sweeping the voltage as you measure the current. Sometimes you might want to sweep backwards from high voltage to low voltage, and then what you notice is that the direction, the plot looks different, going this way versus going that way. And this has to do with some complicated physics that essentially, in order to avoid, and this causes problems, of course, right? Because you don't know what the efficiency is because you've got two different measurements. So to avoid this, you need to reduce the rate of the voltage bias. In other words, you need to sweep very slowly so you get a DC measurement, or measure the current at a fixed voltage, essentially completely DC measurement. Something to be aware of. You also have things like light soaking issues. So there are nonlinear effects that happen, particularly with some thin film cells. In that, what I mean by that is that sometimes the efficiency actually changes with the amount of light that illuminates the cell. And this typically happens when the cells are just made in a factory. In fact, I visited a factory based in California many years ago, and they have sections where they simply let the solar cells sit under very bright light like this for a long time, so it stabilizes and reaches a specific efficiency value. Otherwise, it's very hard to give a value to your customers. So this is part of the quality control protocol that people use. Of course, when you measure these things, you have to be aware of series resistance incorporated by the contacts. Typically, the contacts are based on these bond pads that you can see here, of course, which is not a perfect contact, right? So there is always resistance. And these show up as series resistance, and that can artificially lower the efficiency of a cell. So to avoid this, typically people use something called 4-probe measurements to get more accurate results. So in a standard quality control procedure in a factory is to do 4-probe measurements on all the cells that are made. Next, I want to spend a little bit of time on the instrumentation used to actually illuminate the solar cells themselves, which is the solar simulator that I alluded to briefly before. Again, the idea is that we want to measure current voltage characteristics of a solar cell while it is under some sort of illumination. Now, when I say some sort of illumination, we want to be able to control it. So how do you control it? That's what I want to talk about. Oops. We control it with something called a solar simulator. So this is the a schematic of a commercial solar simulator that you can purchase. It's somewhat expensive, typically in the order of $10,000 to $15,000, based on or more, based on how accurate you want it to be controlled. But typically, you have something like a xenon lamp, as shown here, with a parabolic or an ellipsoidal reflective mirror, so all the light goes in a parallel fashion. Then your mirror shown here to bend the rays, so the light comes straight up, it's bent this way. Then you have something called an integrator, which is to ensure that the beam is very homogeneous and smooth. And then you have a shutter. And then you have some sort of spectral correction filter, so the light passes through. After correction, it looks more like the spectrum of the sun, and that's very difficult to do, by the way. And then you have another mirror which sends the light down. And then you have a collimating lens, which essentially makes sure that the light is essentially straight coming out or collimated. And the working plane is where you place the solar cell. Okay. And now each of these components can be very complicated and have to be very carefully designed. The choice of the lamp is, of course, one of the first things to keep in mind. There are many choices for lamps. They all have different spectra. For instance, this is the quartz tungsten lamp shown here. And in comparison, you can see the AM1 direct spectrum there. So we are trying to match this clearly with a single lamp, and it's very difficult to do. With the filter, you can get somewhat close, as shown by this curve here. You can also use a mercury lamp. Unfortunately, mercury has lots of peaks. These sharp peaks are not very good for solar cell measurements because it causes a lot of artifacts when you try to match to the solar spectrum. However, a metal halide lamp is sometimes good because you get enough light in the UV, which sometimes is useful to understand the loss mechanisms in solar cells. So there are lots of different choices for the lamps. As I said before, quantum efficiency is a very important metric for solar cells. So how we measure this is important. Again, to remind ourselves, quantum efficiency is the ratio of the number of charge carriers, the electron-hole pairs, collected by the solar cell. By collected, I mean those contributing to the current generated by the solar cell, divided by the number of photons of a given wavelength incident on the solar cell. So you measure this for a particular wavelength of light, and then you sweep the wavelength, you get the quantum efficiency as a function of wavelength. So typically you have a plot which looks like that, which plots lambda. Oops. Which plots lambda here and quantum efficiency here. Typically, what you typically see is something like that, but we'll see some examples shortly. In other words, when the lambda is too long, then the photons don't have enough energy, or if the lambda is too short, then most of the energy is lost by thermalization. So in between, you have this nice ideal lambda, which is close to the band gap of the material, typically. This is an indicator of how good a solar cell is at converting sunlight to electricity. And ideally, a solar cell should have high spectral response at the wavelengths where there is abundant number of photons in the incident sunlight, which is, of course, common sense. And this is an example of what the quantum efficiency looks like. Again, the wavelength is plotted on the horizontal axis. This is percentage, which is what the percentage of photons that are converted to electrons and contributing to current. So at very short wavelengths, the quantum efficiency is reduced at short wavelengths due to surface recombination, which are basically defects at the surfaces of solar cells. Those will trap the electrons, very similar to the lattice defects that I talked about before. At very long wavelengths, you have other problems, things like reduced absorption, which we've talked about quite a bit. There's something called low diffusion length, which has to do with the fact that if it's absorbed at very deep inside a material, the electrons and holes have to travel far to reach the terminal. However, if there are defects in the material as it's traveling, then these can get trapped and won't reach the terminals and contribute to current. Similar thing happens with the rear surfaces where there are defects as well. So you can avoid this with passivation, which is what that's talking about. So that's what this decreases. Then in between, you have a slight reduction in QE due to reflection, transmission, and lower diffusion length. This dashed line here is the ideal solar cell, where you want to get 100% of absorption, 100% quantum efficiency, until it gets to the band gap below which it's 0%. So that's the ideal case, which of course does not exist in real life. So just to summarize this, when all photons are converted and collect as charge carriers, the quantum efficiency is 100%. With photons are energy less than the band gap, the quantum efficiency is 0%. So out here, of course, is 0 no matter what. It's generally reduced due to recombination. Blue light is absorbed close to the front surface. So recombination of the front surface will affect quantum efficiency at blue wavelengths. Green light is absorbed mostly in the bulk of the solar cell, so low diffusion length will lower the quantum efficiency of green wavelengths. At redder wavelengths, the lower efficiencies, surface recombination at the rear surface, as well as lower diffusion length will lower the quantum efficiency. So this is something called internal quantum efficiency. External quantum efficiency includes the effects of optical losses, such as transmission through the cell, as well as Fresnel reflections away from the cell, which is the top. So remember, if this is glass and that's air, you have some of the light reflecting off, approximately given by n-1 by n+1 squared, if you recall. This is the Fresnel reflection loss. Internal quantum efficiency refers to the efficiency after excluding the transmitted and reflected light. Only the absorbed light can generate charge carriers and in turn generate current. Now, the principle of how do you measure this? So in order to measure this, you have to do some careful experiments. And that's the last topic I want to talk about today. So first of all, we recognize that the band structure in a semiconductor is wavelength dependent. So different wavelengths will get absorbed differently. Again, photon with energy above the band gap is absorbed, energy below the band gap is not. An absorbed photon creates an electron-hole pair, which, if it reaches the electrodes, creates current. To calculate the quantum efficiency, we need to know the incident power in the cell and how much current is produced at each wavelength. The currents produced by a test cell and that by a calibrated photodetector are measured, and the ratio of these two is essentially called the cell responsivity. The quantum efficiency, again, its definition is simply the number of charge carriers divided by the number of incident photons at a given wavelength, lambda. Number of charge carriers is simply the current measured divided by the electronic charge. E is if you recall, is 1.6 to 10 to the minus 19 volts, right? That's the charge of an electron. And so a very small value. So this ratio here gives the total number of electron-hole pairs. And this ratio here, this is the energy of a photon. So this ratio here gives the number of photons. Because it's the energy of one photon, total incident power ratio gives the number of photons. You do the same measurement for the reference detector, which gives you the reference photodetector responsivity. And from that, and with the measurement under the source spectrum, you can actually compute the quantum efficiency. So this is the measured from the actual cell, multiplied by the reference responsivity, which is typically given by, when you purchase a certified reference cell, you have that. This because it's the wavelength of light you use to illuminate it. And this is also given, this is a constant electronic charge, E here. And this last I reference is also given by the material, certified solar cell. So for example, this is an example setup used to do these kinds of measurements. They're somewhat complicated because the amount of current you get is very low because you're only sending in one particular wavelength of light. So first of all, you have something called a monochromator, which selects the wavelength of light. You're able to send in a single wavelength of light. Then there's something called so that goes this way. Then there's something called a, oops, sorry, it goes the other way. So here is the source, right? This is the light source. Light goes this way. There's a filter to select some wavelengths. Then it passes through this way. The monochromator selects a single wavelength, comes out through this fiber, and then it illuminates the solar cell. And there is a calibrated reference detector shown here. There's something called a chopper, which does a phase lock loop measurement. Simply the chopper chops the beam at some very high frequency, and which means that your incident light has some very high frequency, which looks like that. And as expected, the solar cell will produce current, which looks like that, right? And by matching the frequency of this current to the frequency of the chopper, you can get very, very sensitive low SNR measurements of the current. I won't go into the details, but the design of this monochromator turns out to be pretty complicated, but it's a little bit, I think, not relevant here, so I'm going to skip this stuff. Yeah, so I think that I'll stop here just to mention that the amount of light that you send in is very low because you're sending in only one wavelength at a time. So the amount of current that you're getting out of the cell is also very low. So that's why you need to do this lock-in amplifier approach to doing the measurements very carefully. Okay, with that, I will stop here and see if there are any questions. If not, let me just remind you that let's stop here today, and let's remind you next week is Thanksgiving, of course, but we do have a lecture on Thursday and Tuesday, and but no lecture on Thanksgiving Day, obviously. And the following week is assignment 6, which is December 3rd, so just be aware of that. And well, thank you. And if you have any questions, certainly ask on Slack. Okay, let's see if we can. Okay, thank you, everyone.